Hello, we have come to the second half of this course, which is Introduction to Detectors. And in this course, we are going to basically look at optical detectors. So you will see clearly that the study of detectors is mostly a study of noise because the intrinsic detection process itself is statistical and it always comes with noise. So what exactly is a detector? What you have is an element that is connected to an external circuit. And in this element, when the light strikes, the energy of the light is absorbed by this material, and there is a change in the current that flows in this external circuit connected to this particular element. Uh, there could also be a change in voltage, and you are familiar with detectors of this kind, which could be, for example, a photodiode, which is a PN junction wherein the a number of carriers are changed as the light strikes on that piece of PN junction, and hence when it's connected to an external voltage, there is a electrical change in terms of either current or voltage. The other kinds of detectors could be a change in electrical resistance. These are extremely sensitive detectors called bolometers, where what you have is a small cavity in which once the light strikes, there is a local change in temperature, and that change in temperature is translated into a change in resistance of the material, and that is what is detected as as a response to light. There are other types of detectors wherein, for example, electron is ejected when the light strikes on it. You have learned about these kind of phenomena very early on. This is what is photoemission, uh, based on something called the photoelectric effect, if you recall. So there are variety of such detectors, and one of the main things that we want to deal with in this course is limit ourselves to optical detectors. We will not talk about other kinds of detectors. And in terms of applications, detectors are everywhere. The moment you have any source, you need to have a detector, whether it's optical communications, interferometry, material processing, name the device, and every device will have a signal and a response. And to measure that response, you usually require a detector. So now let us look at the characteristics that one would like in an ideal detector. So these are some of the characteristics that I have listed out. One would like that the detector is highly sensitive. That would mean that it can detect even low levels of the input signal. One would like that the detector has a one-to-one correspondence between the response, which is directly proportional in a sense to the input signal. This is because we would like to make quantitative measurements out of the detector. That would mean that as I vary the levels of the signal power, I want the corresponding variation in the detection process. One would probably want the detector to have a fast response. That would mean that if I change my signal, or if there is a change in the signal, the detector responds instantaneously to that change. So this is a kind of characteristics that is extremely desirable in a detector. Similarly, one would require the detector to have a response which has wide bandwidth. What that means is that I would like the signal of a variety of wavelengths to be detected by the same detector. So typically you see that the detectors will have a limited range within which they are sensitive to the signal, but in an idealized situation, one would like an extremely wide band detector. The other very important characteristics is the business of noise. We would like our detector to be robust against noise, simply because if you look at the microscopic level, the detection process itself is governed by quantum mechanics, which, as you know, is a probabilistic theory. So the notion of detection itself is statistical, and plus the fact that the detector is connected to the environment, there are other sources of noise that affect the ability of the detector to give you a response which is only limited to the response from the signal. So our detector, usually all real detectors are going to be limited by this noise that is uh, inbuilt in the process of detection. So this is an important statement I want you to keep in mind. The detection is intrinsically a statistical process. It is always going to be accompanied with noise and fluctuations. So we are going to deal with optical detectors. So these detectors usually are in the class of something called the square law detectors. What that means is I'm going to actually measure the energy content or for example the intensity of the incoming signal and not the electric field per se. So what we are going to measure, particularly in the optical regime, it is not merely the electric field square. One averages over the response time of the detector. So what we always detect is the square of the electric field itself. And hence, these are called square law detectors. Of course, there are some microwave detectors that do measure the electric field directly, but at the moment we will not worry about them. And there are two major types of optical detectors. One of them is the photon detectors. The other one is a thermal detector. So the photon detectors are usually limited by there is something called a long wavelength cutoff. What that essentially translates in is that there has to be a minimum amount of energy in the signal, okay, in the quanta of the signal, such a way that that minimum energy is required for it to be detected as a signal by the detector. And that leads to a, 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 a minimum in the frequency cutoff, or in terms of wavelength, it gives me a long wavelength cutoff. Similarly, there are thermal detectors which are based basically on the fact that the energy that is coming in is eventually going to be absorbed by the system. And because this is absorption and it essentially behaves like a black body which absorbs everything, so really the response is not limited necessarily to a definite cutoff, because eventually the photon or the signal bounces back and forth and it's going to be absorbed until that absorption turns into a change in the local temperature. So these are thermal detectors and they are largely independent of the frequency or wavelength. So here you have graphically the response of photon detectors in contrast to thermal detectors. So for example, you can clearly see for the photon detectors, there is going to be a definite uh, cutoff, long wavelength cutoff, that I indicated this by as lambda c here, beyond which the signal, there is no response from the detector. In contrast, you have the thermal detectors, which, as I said, largely rely on um, notions of black body radiation, where there is a broad absorption of radiation across wavelengths and so on, because there what you have is the energy absorbed eventually turns into a change in the temperature, and that temperature change is what is being recorded or measured. So, so these detectors are largely, are not limited by. um these detectors are largely broadband and are not limited like the photon detectors in terms of wavelength. So now let us look at the process of light absorption and detection. So what we have is a power that is input. I'm calling that P in. Now this power falls on the detector. There is a finite volume of the detector through which the power or the signal needs to propagate before it is absorbed completely. So what we need to keep track is what is the amount of power that is absorbed as it propagates through the detector. And not just that, we assume that for every photon that comes in, there is one charge carrier that is generated. So one eventually gets a relationship between the the power in, right, and the the photocurrent that is generated. So IPH here stands for the photocurrent. The ratio of these two quantities is what is called as the responsivity. We will talk about responsivity slightly later. So this form of the responsivity is what I will discuss next. So here I have the finite size of my detector material, right, indicated in this box. And what I have is the power input from the left. And you see that uh, because of the finite mismatch between the refractive index of the medium on the left to the refractive index of the detector, there is a finite reflectivity that one can associate it with this interface. And you see that the input power is reflected off by this finite reflectivity or the finite index mismatch between the signal and the detector region. So what actually remains or goes into the detector at z equal to 0 is basically 1 minus r times p in. And this power gets exponentially absorbed as the signal propagates through the detector. So you see that this is the kind of power that is being absorbed, and this quantity which I've indicated here is basically the remnant power after absorption. So now if you ask what is the power absorbed, it is simply the power that was input minus the power that is that is remnant. So you will get essentially what is the power that is absorbed. So if you put this together, you will actually get the expression which I indicated earlier. But before I do that, let me just carefully look at this exponential decay or absorption. You know the uh, Lambert-Beer's law, which relates the intensity at a particular point z to intensity at z equal to 0 times exponential minus alpha z. Here alpha is the absorption coefficient. We also dealt with the absorption coefficient in great detail in our previous part of the course. And z is the distance it travels from the starting interface towards the depth of the detector as the signal propagates within the detector. And of course, capital R here is the reflectivity. So the equation 1 can be rewritten in this form, right? So you have the photocurrent being generated because of this power which is essentially absorbed, right? So this is my power absorbed, and you see for you look if you look at the power, you see that is essentially the amount of energy per unit time. You can think of energy uh, per unit time as also equivalently the number of photons, uh, energy per photon times the number of photons per unit time, right? So what I've done is to divide this by h nu, which will basically give me P in by h nu will now give me the number of photons per unit time. And what one is saying is that for every photon, a charge Q is being generated, right? So you see that Q by h nu essentially, tells me that for every photon of energy h nu, a charge Q is being generated, right? So this relationship, you can clearly check its units. This relationship gives me the relationship between the input and the response, the input being the optical power in and the response being the photocurrent in the external circuit that you generate because of the presence of the input signal. The ratio between these is what we call as responsivity. This is sort of a figure of merit for a detector. Larger the responsivity of the detector, greater is going to be its sensitivity. So you can clearly see that, for example, it is measured in terms of ampere per watt or microampere per microwatt or milliampere per milliwatt and so on. What it tells me that is what is the amount of current being generated, photocurrent, because of a certain amount of input power measured in watts. Now you see, this has clearly got to do with my uh, with the notions of the input photon and its energy, the the generated current and the charge and so on. Um, so you see, there are some intrinsic properties that we can associate it with this device, which is simply this factor of 1 minus r times this exponential factor 1 minus exponential minus alpha z, right? This is a characteristic that completely characterizes the detector material, right? And to in if you think about it, what one is asking is on that you have the amount of photons which are coming in, right? So P in by h nu is giving you the number of photons which are coming in per unit time, and I photocurrent by Q is giving me the essentially the number of charges that you're generating per unit time. So the ratio of these two numbers, that is the number of photons coming in and the number of charges being generated, this ratio is what is called as the quantum efficiency. It is characteristic of that intrinsic the characteristics of the material being used and in the process of detection, right? So that is why it is called the quantum efficiency. Now this it essentially relates the efficiency of conversion, that is how well does one convert a single photon, right, into a single carrier. That efficiency is essentially captured by this ratio, as I mentioned, and this is what is called as quantum efficiency. Now we can clearly see one can improve the quantum efficiency, which is by making sure that the signal coming in and the detector material is index matched, so that the reflectivity is minimum. That would mean that more and more of my signal will get into my detector. The second important thing is that you see the energy is absorbed exponentially. That would mean that at any distance there's going to be a small remnant amount of energy anyway. So one would like a thicker detector to make sure that any energy that comes in is completely absorbed by the system, right? So one would have to also look at now absorption coefficient, and thus the distance the energy needs to travel before it is absorbed and is registered as a signal. So clearly, the quantum efficiency process does not account for losses that might be there otherwise. For example, you might generate a carrier, but it is trapped in the surface states of the detector and hence not recorded as a signal in my external circuit, right? So there are going to be issues of that kind which I have not really accounted for. When it's simply looking at the bare fundamental notions of the material characteristics of the detector, that is what this quantum efficiency essentially quantifies. So now let's talk about the absorption coefficient. Now you see the absorption coefficient clearly is a wavelength dependent quantity. We have seen that even earlier in this course. So for example, I have given you numbers here for silicon. Alpha inverse gives me a length scale, which basically tells me that larger the alpha inverse, lower is the absorption, right? So for example, at 700 nanometers, the you need to travel, let's say 5 micrometers inside the silicon crystal for it to register as a, for example, a signal. uh, if you come up with a higher energy, you need to travel much shorter distance, right? Because the absorption is much larger, and hence alpha inverse gives you a quantity, a length scale which is much smaller. So you see, this is a typical characteristics of this photon detectors, where there is a wavelength, long wavelength cutoff. Um, that would mean that if you associate an energy which is smaller than that, then one will not register that as a signal. So for example, I've obtained this expression between lambda c, which is the long wavelength cutoff, to the band gap in a semiconductor detector. So for example, if I just equate Eg to h nu, which is the minimum photon energy required for it to be registered as a signal, so you see that you can come up with this relationship. And on the right, all that I have done is to put these numbers for h and c, if you plug in these numbers of Eg in electron volts, you can actually get the wavelength cutoff in micrometers. Now, one thing very important to note, that when you talk about alpha inverse as a length scale, what one is telling is that if you look at about 2.5 times the absorption length, basically 90% of the input energy is going to be absorbed, right? So all that one is asking is, how much energy is going to be absorbed as you propagate further down into the silicon material, for example. And if you travel 5 times absorption length, then 99% of your input signal is absorbed. So that's a way to think about absorption coefficient and the length scale associated with the process of absorption. So now you see, I can rewrite this responsivity, right, in terms of wavelength. So all that I have done here is, in my denominator, I do have the photon flux. Hc by lambda is simply h nu. So this essentially is I photon, or rather the photocurrent that is generated, right? And it is divided uh, by the input power, right? So if you rewrite this and you take the lambda on the top, you see the responsivity clearly is a linear function of the wavelength, right? I will come to this process of this gain a little later, but essentially, this is what we have seen here. E I represented as Q earlier, so E is the charge, electron charge. Eta is essentially the quantum efficiency, and phi is the photon flux. All right. So that is how uh, one is looking at the relationship between the input, in this case the photon flux, and the generated photocurrent, right? So you see that if I can basically, you have this straight lines drawn here. This is a curve that between the responsivity and the wavelength, and you see these straight lines correspond to certain quantum efficiency. Clearly, as you decrease the quantum efficiency, right, you see that uh, the slope actually also correspondingly decreases with respect to this wavelength graph. So as I mentioned, for example, you know uh, the the silicon has got a certain band gap. That would mean that this value would correspond to roughly the long wavelength cutoff. Similarly, germanium, this would be the long wavelength cutoff. You can also have combination of materials like indium gallium arsenide. We will talk about them. We will see that silicon is a indirect band gap material. So there is it is not necessarily used for generation of light, but it is used as a detector, certainly, and so on. Now there is this term which is the gain, right? This is what I want to discuss. I will discuss that in the next slide, but let me just briefly tell you what it is. It is basically, it's a ratio of two time scales. One is the time taken for the you generate the charge, right? When you detect, you generate a charge, and you see there is a loss of charges, that because these charges can recombine, and that signal is lost from the external circuit where the charges are supposed to flow, right? So this is the time scale of the lifetime, essentially, or the rate at which the charges are being lost because of recombination. On the other side, there is a time scale which is telling you the time required for the carrier to move across the semiconductor, the block, which is connected to the external circuit, the time required for it to travel from one end to the other, essentially, because that limits how quickly I can register something as a signal in my external circuit, right? So we will come to that a little bit in detail, but the ratio between these two essentially gives you the gain in the system, uh, right? So we will, let's see how that comes along. Uh, so again, I come in with the incident photon power represented by P, right? Then I have a quantum efficiency, which is eta, and you see that efficiency tells me that intrinsically for what is the probability of, or rather what is the percentage chance that for every input photon I'm going to generate a charge, right? Corresponding carrier is being generated. So my incident photon power divided by h nu will give me the number of photons per unit time that are coming in, and these photons times eta, which is the quantum efficiency, tells me the rate at which the carriers are being generated, right? Similarly, the carriers are being lost due to recombination, right? These they are basically, you are creating electron hole pairs, and these can get lost, right? They can recombine and so on. So you see that there is a rate at which they are getting lost. So if you look at the carrier dynamics, which is to write down, for example, a rate equation, right? dn over dt, where nc is the number of carriers we have generated. So you see that it is simply interplay of two phenomena. One is the generation rate, which is governed by the quantum efficiency and so on, and one is the loss rate. So in steady state, of course, you continuously imagine that your signal is fixed, power is fixed, hence the signal is fixed. So in steady state, you see that dnc over dt is 0. That gives you that your nc is, is governed by something like this. It has got the rate at which the carriers are being generated multiplied by the lifetime of the carrier, which is a lifetime of survival, essentially, of the carrier before it recombines. And we know the following, that the current in my external circuit, right, because of an electron, is simply given by E times V by D. V being the velocity with which the the electron moves across the semiconductor block. So you see that your velocity, which is, you can you can think of this as the effective, it's not really ballistic. There's the effective velocity of the or the drift velocity of the electron going from one end of the detector material to the other end. So you see that this drift velocity by d will essentially, give me 1 over time, and that gives me the current because of the electron. So you see that the photocurrent which I generate is simply the current due to one electron, which is IE, times the number of carriers, right? Which is what gives me the total photocurrent, which I can rewrite, and you will clearly see, the similar form that we got earlier. We have the power, we have E times or Q by h nu, as we had described earlier. Eta is the quantum efficiency, and there is this fraction of Tr over Tz, which is very important to realize. This is precisely what I was mentioning. It is two time scales. One is Tz gives me the time scale, the time required for the electron to drift across the length d, which is the thickness of the semiconductor detector material, and Tr over Tz, if this is greater than 1, I'm essentially going to generate more than one carrier for my input photon. What that means is, remember that my detector block is charge neutral. So imagine I quickly go across, electron quickly goes across the detector, goes into the external circuit. Now you see that because the electron has gone out of the semiconductor material, it needs to draw another electron from the connecting wire on the other side. So you see that this maintaining it to be charge neutral is going to now draw in more electrons for the same uh, electron that had actually gone out of the circuit, right? So this kind of thing is what is actually generating, sort of gain in the system, where you are creating more number of charge carriers, right, for that single photon that came in, right? So one has to, that is why there is a gain term associated with that. The other kind of uh, detectors are the photovoltaic ones. So for example, the PN junction, like photodiodes, these are photovoltaic. Um, they may or may not require an external bias. For example, in a solar cell, you generate without an external bias, you actually create a voltage difference when light falls on it. So these are again PN junction appropriately operated. And there are these fourth kind of detectors, which are like bolometers, which are basically sensitive to temperature change due to absorption. So once you have a material, you know, which can eventually absorb everything, you see that that energy is transformed into heat, and that heat changes the, for example, resistance of the material, and that change in the temperature is essentially registered as uh, the change in the electrical characteristics, like the resistance being dependent on the temperature changes, and hence that is how the detection process happens. So we will look at some of that. And the next thing, I'm going to focus on these very important aspects related to the figure of merit of a detector. What it tells me is that once you, for example, you are involved in a particular experiment where you want to focus and try and come up with a correct detector for your signal. So you will have a choice of detectors, and then you will look at what exactly you want to detect and choose figures of merit associated with the detector characteristics that are matched with your requirement, right? So this ability to basically read that data book about the characteristic of a detector, its technical content, is what I want to cover quickly for you to understand what you're dealing with. So there are a variety of figures of merit. So we will go through them one by one. So for example, the simplest variety is indeed, the responsivity, which we already looked at. A responsivity, higher the responsivity, um, better is your detector. What it tells me is that the amount of, it is a ratio between the photo current that you generate and the input power. So larger the photocurrent you generate for the same input power, you have larger responsivity, and hence this is a figure of merit, which is, as I mentioned earlier, it is measured in terms of watts, or other amperes per watt. That's the number of amount of current generated for the input power in watts. Uh, a similar figure of merit is also called the spectral responsivity. And clearly you see that depending on the wavelength of your input signal, the response is not going to be exactly equal. So because the responsivity is wavelength dependent, one can also talk of something called the spectral responsivity, which simply tells me the operational wavelength at which a specific responsivity should be looked at, right? And clearly, this figure of merit does not talk about noise. As I mentioned, it is measured in terms of ampere per watt, or even, for example, volt per watt. And this is the kind of one notion of a figure of merit. So what it basically comes down to is, understanding what is the level of power levels that you have. For example, and what is the level of electronic circuitry or its sensitivity that you want to maintain, so as to detect that that change in that current that you expect from the corresponding input power levels. So that is the kind of thought process that needs to go in to choose the appropriate responsivity for your detector. The next important figure of merit is something called the noise equivalent power. So what it is telling you is that what is the weakest value of the signal that you can barely detect, because below that you will be submerged in noise, right? So this noise equivalent power, clearly it basically gives me the baseline of noise. The lower the noise equivalent power means greater is the sensitivity of your detector, right? uh, so now this noise equivalent power is given in terms of uh, you know uh, it it basically tells me, essentially it is given in terms of watts per square root hertz. Here I in is the photon intensity of the input intensity, if you like. A here is the area of the detector. Intensity is power per unit area per unit time. Multiplied by the area of the detector, the area goes away. So it's basically, you know, uh, just power or energy per unit time. And then you see that this Vn over Vs is basically the ratio of the noise and ratio of the voltage associated with the noise, and the ratio and the voltage associated with the signal. That ratio is precisely this Vn over Vs. And it also is multiplied by the uh, inverse of the square root of the bandwidth, right? So I'll come to how operationally one should think about this. Typically the reference bandwidth is 1 hertz, uh, and you can clearly see that this noise equivalent power actually depends on the area of the detector, right? So that would mean that if I want a wide area detector or a small area detector, and I want to compare the material but not the area, obviously the larger area is going to detect more signal. But if I want to compare material, the noise equivalent power is not a good measure because it depends clearly on the area itself, right? So one has to be very judicious in choosing what figure of merit and understand in what context that is used. But it is giving you a measure of the noise equivalent power. The next slide gives you the example of this noise equivalent power. So for example, let the detector specification be such that it is talking about, for example, uh, the specification says that it is 6 picowatts per square root hertz, and it can go from this DC to about 100 megahertz is the kind of range it can detect. So this is the NEP, for example, specified to you uh, by the manufacturer. So what it tells you is basically the following, that if you put in a signal of 6 picowatts, that will be detected with a signal to noise ratio of 1 for half a second of averaging time, right? Within this 1 hertz bandwidth. So what it is basically telling you, why the half a second, is because you see that the averaging time T average is equal to 1 divided by 2 times the bandwidth. Um, so you see that because I have written here my bandwidth is 1 hertz, so you see that my T average tells me the averaging time. uh, if you have about half a second, in that case, you will detect this 6 picowatt with signal to noise ratio 1. Now you see, if I want to now improve my uh, if I want to detect a signal which is of a lower strength, what do I do? So what I do is basically average over, for example, for a larger time. Let's say I average over 50 seconds rather than half a second. So you clearly see that my bandwidth there would become 10 to the power of minus 2. So that would mean that I have to just take my 6 picowatts, okay, per square root hertz, multiplied by uh, you know the bandwidth, which is 10 to the power of uh, so if I just multiply by the square root bandwidth, I would clearly see the minimum power that I can detect now is going to be 1/10 smaller. It's going to be zero point 0.6 picowatts. So that is essentially how one should look at. By increasing the averaging time, right, one is then correspondingly decreasing the bandwidth. So if this is given as, 6 picowatts per square root hertz, I can simply multiply by the square root of the bandwidth and obtain the corresponding minimum power detectable if I start averaging anything other than half a second, right? So that is how one uses this noise equivalent power figure of merit to choose a detector. Or rather, once you have chosen a detector, you can basically figure out, to detect a certain level of power, what is the averaging time you need for that power to be detected. The other figure of merit is the notion of detectivity. So detectivity is simply, it's an inverse of noise equivalent power, but it is multiplied by the square root of the area. And uh, this actually makes, this is known that this actually makes this detectivity to be independent of the area of the detector. So even though in the noise equivalent power we had area explicitly coming of the detector, but actually it depends on the square root of the area. Hence the square root of the area gets cancelled here, and what you get is this D star, which is called the detectivity. Now clearly, detectivity is larger the detectivity, better is a detector. Unlike the noise equivalent power, where smaller the noise equivalent power, better was a detector. Here higher is better. This is a quantity which is independent of the area, and because it is such a quantity that doesn't depend sort of on the design, but it more depends on the intrinsic quality of the material involved in the process of detection. And clearly you see that its units are centimeter or length multiplied by square root hertz per watt, right? Because remember, watt per square root hertz was the units for NEP itself. So this is the inverse of that. And again, as standard, the reference bandwidth is usually taken as 1 hertz. The other figure of merit is the quantum efficiency, right? It is basically the ratio of the number of carriers generated by the number of photons incident, and this is something that we have already discussed earlier, right? So the next figure of merit is something called the speed of the detector response. That is, you're coming with a signal, okay, and you're asking how long does it take for the detector to actually respond to that particular value of the signal. How long, how quickly does it do that? So for example, the response time or the rise time of a detector is is the is the time required for the detector to rise, from, let's say, the off level to the on state, but only the 63.2% of the value of the steady state on state. So for example, the steady state on state was 1 volt. The 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 time required for it to go from 0 to about 0.63 volts is precisely the response time or the rise time of the detector, right? Similarly, there is a recovery time. That is, when the signal goes off, how quickly does the detector come back and get ready for the next event to be detected. So this time for the photocurrent to fall to about 36.8% of the steady state value of the off state is precisely called as the fall time. So there is a rise time and there is a fall time, which characterizes the speed of response of these detectors. Now, clearly, a detector doesn't work in isolation. The detector is connected to an external circuit, and the the load resistance, the capacitance, the RC time constant of the external circuit essentially also determines the speed of response of the detector. So one should not look at the detector response speed as in isolation. One also needs to carefully now design my external circuitry so as to get the fastest response that you might require. And one important caveat is that the speed of response and the sensitivity, these are always going to be two characteristics, that cannot be both satisfied simultaneously. They are going to be, you need to choose one over the other. So uh, either you choose the speed of response and then hence you compromise on sensitivity, or the other way around, you want high sensitivity. That would mean you certainly want the signal to be absorbed within the a large region of the detector and so on, uh, and hence correspondingly your speed at which you can respond decreases. So these are the usual trade-offs that you need to keep in mind, and they play an important role. The next figure of merit, probably the last one, is basically the linearity of the detector response, right? So you see that the detector operates from all the way at the very low noise level all the way to saturation. What saturation means is that beyond a certain point of the input power level, the detector somehow doesn't respond linearly to the changes in the signal. The response generated by the detector has saturated, right? So between this, remember we demanded that the detector be such that it produces a one-to-one correspondence between the input signal and the response. So hence what one is asking for, how linear is that response? So the maximum percentage deviation is how we specify you know the linearity of the detector. For example, let's say you have a detector that can detect from 10 power minus 12 watts per centimeter square intensity to all the way to 10 to power minus 4 watts per centimeter square with a linearity of 5%, right? What that means is that literally you can detect 8 orders of magnitude, and your one-to-one correspondence between the a fit of the line in these 4 orders of magnitude is going to be a straight line with a variation at most or about 5%. So that is the kind of figure of merit of linearity that one talks about when one talks about the various figures of merit uh, for a detector. All right. So in the next lecture, I'm going to essentially, talk about noise characteristics. So I have sort of finished these figures of merit, which is important for you to have an ability to choose the correct detector and understand technically, what are the various uh, inputs that you need to consider, or the various characteristics of the detector you need to consider before choosing one of the right kind for your specific application.